Hello, my name is Rohan Kadekodi. I am a PhD student at the University of Texas at Austin, where I work with Professor Vijay Chidambaram. I work on persistent memory storage systems. Today, I will talk about WineFS, a huge page-aware file system for persistent memory that ages gracefully. Optane DC persistent memory is a new memory technology by Intel. It is a non-volatile and fast medium, meaning that it can retain data across power cycles and has access latencies similar to that of DRAM. There are two ways in which applications primarily access their data on persistent memory. The first way is through POSIX system calls. Legacy applications access data by issuing read and write system calls to the underlying persistent memory aware file systems. The second way of accessing data is by memory mapping files. Due to its unique characteristics, newer applications that are developed on persistent memory try to access data directly from user space without entering the kernel. These applications are called memory mapped applications. The applications first allocate space on persistent memory using fallocate or ftruncate calls to the underlying persistent memory aware file system. The applications then memory map the files into user space. In the presence of a feature in the Linux kernel called DAX or direct access, there is no data copy from persistent memory to DRAM on memory mapping a file, and physical addresses on persistent memory are directly mapped to virtual addresses in the application's address space. After mapping, the applications perform direct loads and stores to the allocated space on persistent memory from user space without going into the kernel. Page table mappings are used to convert virtual addresses to physical addresses on PM. The first access of a page leads to a page fault that sets up page table entries. Frequently accessed pages are cached in the translation look-aside buffer for reducing address translation overhead. Page faults take as much as 60% of the time of memcpy when the memcpy is of 4 kilobytes. The performance of memory mapped applications thus depends on the number of page faults and TLB misses incurred by applications while performing loads and stores in the runtime. In order to alleviate the overhead of page faults, modern hardware and kernels support huge pages, which are basically larger pages of 2 megabytes or 1 gigabyte in size. Huge pages reduce the number of page faults and TLB misses by up to 500x. A file needs to be allocated using 2 megabyte contiguous as well as aligned extents in order to be mapped using huge pages. For example, the file on the left here is not contiguous in 2 megabyte extents and cannot be mapped using huge pages. The second file is contiguous in 2 megabyte extents, but is not aligned to 2 megabyte boundaries, and again cannot be mapped using huge pages. Finally, the file on the right is aligned as well as contiguous in 2 megabyte extents and can be aligned and can be mapped using huge pages. File systems in this way are responsible in issuing huge pages for memory mapped applications. Another important point is that file systems must preserve huge pages or 2 megabyte aligned extents with age. This brings us to the next topic. What is aging and why should we care? Aging is the state of file systems as a result of constant allocations and deallocations over a long period of time, typically years. Google, in their talk about cluster storage systems, mentioned that they want to keep disks full and busy in order to avoid excess inventory costs. The figure on the left shows their disk utilization, where every box is a disk and the colors show disk spindle utilization. As we can see, majority of the disks are almost completely utilized and the free space is extremely fragmented. Thus, aging leads to fragmentation of free space, increasing the number of page faults in memory mapped applications. For measuring the impact of aging on different file systems, we perform a simple experiment where we memory map a 1 GB file and perform sequential writes using memcopies of 4 kilobytes each to the file. The y-axis shows the bandwidth of memcopy commands where higher is better, and x-axis shows the utilization of the partition on which we perform the experiment. When freshly created, ext4 is able to achieve a bandwidth of greater than 4 gigabytes per second. However, when aged, the bandwidth of memcopies on ext4 DACs drops as the utilization increases, and at 90% utilization, the bandwidth of aged ext4 DACs drops by more than half compared to freshly formatted ext4 DACs. Similarly, the bandwidth of Nova drops when aged, especially at higher levels of utilization. So, aging significantly degrades the performance of state-of-the-art file systems such as ext4 DACs and Nova. In order to solve this problem, we present WineFS, which is a Hugepage-aware file system for persistent memory that ages gracefully. WineFS uses a novel alignment-aware allocation policy to preserve huge pages. WineFS achieves high performance for a wide range of applications that access files using memory mappings as well as POSIX system calls. WineFS is designed to achieve high scalability and works well with multiple NUMA nodes. The performance of WineFS stays the same when aged. Moreover, in some memory mapped applications, aged WineFS actually performs better than freshly formatted Nova. WineFS is open sourced on GitHub. In the rest of the talk, we discuss about the insights behind WineFS and techniques used by WineFS for achieving high performance. The first insight is that file systems need to allocate files on aligned and contiguous extents in order to be mapped using Hugepages. Existing file systems like ext4 DACs and XFS DACs strive to preserve contiguity of free space with age, but fail to preserve alignment of free space. WineFS uses an alignment-aware allocation policy that focuses on contiguity as well as alignment of free space for allocating huge pages to memory mapped applications. Let us now discuss this alignment-aware allocation policy. Consider that the free space contains fragments that are as follows. The fragments on the left are smaller fragments that are non-aligned, while the fragments on the right are all 2 MB in size and are aligned to huge page boundaries on persistent memory. WineFS maintains two data structures in DRAM for managing free space. The holes or unaligned extents are managed by a red-black tree, while the huge page aligned extents are managed by a linked list. A small allocation request of smaller than 2 MB is forwarded to the red-black tree and is satisfied by a hole. 2 MB allocation requests are forwarded to the huge page list and used up an aligned 2 MB extent. Allocations that are larger than 2 MB are broken down into multiple smaller allocations of less than or equal to 2 MB in size each. All the 2 MB allocations are then satisfied by the huge page list, while the smaller allocations are satisfied by the red-black tree containing holes. A small deallocation request is forwarded to the red-black tree, and if there is a contiguous free extent to the deallocated extent, it is merged. If the merging results in a 2 MB aligned extent, it is moved to the huge page list and huge pages are reclaimed. To summarize, WineFS places large files of memory mapped applications in aligned huge page extents and small files of POSIX system call applications in unaligned holes. WineFS aggressively reclaims huge pages on file deallocations and deletions. The second insight of WineFS is that file systems should achieve high scalability for the POSIX system call applications without causing fragmentation of free space for the memory mapped applications. The per inode log of Nova fragments free space, and the per process log of Strata wastes huge pages by using them up for the POSIX system call applications that do not need huge pages. WineFS uses a suitable on-PM layout, employs per CPU journaling, and a hybrid data consistency mechanism for simultaneously achieving high scalability, strong consistency guarantees, and huge page preservation with age. We now discuss the on-PM layout of WineFS. WineFS divides the entire persistent memory partition into per CPU allocation groups. The super block lies in the first allocation group corresponding to CPU 0. Each allocation group contains its own journal and inode table. The rest of the space in each allocation group is free and aligned to huge page boundaries and tracked by the alignment-aware allocator as discussed before. This design helps WineFS achieve many important properties. Firstly, the per CPU fine-grained journal achieves high scalability compared to a single journal used by ext4, XFS, and PMFS, while avoiding free space fragmentation caused by the per file logs of Nova. Please refer to our paper to check the details of our per CPU journaling. The journals and inode tables are contained to specific regions on persistent memory and do not interfere with the rest of the file system that stores application data, avoiding fragmentation. We next discuss the hybrid data consistency mechanism of WineFS that achieves strong consistency guarantees while avoiding free space and file fragmentation. Consider the free space of an allocation group as shown below, containing free unaligned holes and huge page aligned extents. File 1 is a small file belonging to a POSIX system call application and hence is allocated in an unaligned extent. File 2 belongs to a memory mapped application and is allocated in a huge page aligned extent. As shown before, the free space of unaligned extents is tracked by a red flag tree. On receiving a file update for file 1, WineFS uses copy on write to avoid excess data copies and uses up another hole for the new updated data. Thus, files belonging to POSIX system call applications are updated using copy on write to holes. This avoids fragmentation of free space due to files that belong to system call applications. A file update for file 2 does not copy on write as that will fragment the file and will not allow it to be mapped using huge pages. Instead, a file update for file 2 updates the data in place with the help of data journaling. Files of memory mapped applications in this way are updated in place using data journaling, which avoids fragmentation of the memory mapped files and allows them to be mapped using huge pages. Let us now summarize the techniques of WineFS with their benefits. WineFS uses an alignment-aware allocation policy that takes into account contiguity and alignment of free space while making allocation decisions to files. WineFS uses a suitable on-PM layout and per CPU journaling to achieve high scalability and to avoid free space fragmentation by containing metadata to dedicated areas on PM. WineFS uses a hybrid data consistency mechanism that provides strong consistency guarantees while preserving huge page aligned extents with age. We now discuss the evaluation of WineFS on Intel Optane DC persistent memory. We compare WineFS with other state-of-the-art file systems on a wide variety of memory mapped as well as POSIX system call applications in the paper. We answer three main questions in our evaluation. What is the memory map performance of WineFS when aged? What is the POSIX system call performance of WineFS when freshly formatted and aged? And is WineFS scalable? We answered the first two questions in this presentation. The answer to the last question is that WineFS is able to scale as well as Nova while avoiding free space fragmentation caused by copy on write and per log files of Nova. Let us now focus on the first question, where we evaluate the memory map performance of WineFS in an aged setup. We first check the performance of aged WineFS on the same experiment as before. The performance of WineFS consistently stays at greater than 4 GB per second with increasing utilization. Next, we measure the performance of WineFS on the YCSB benchmark suite run on top of the RocksDB key value store with memory map reads and writes. The y-axis shows throughput with respect to ext4 DACs, where higher is better. And on the x-axis, we have YCSB standard workloads with different read-write ratios. WineFS outperforms other file systems on all of the YCSB workloads. For example, in the load A workload with 100% writes, WineFS outperforms other file systems by approximately 50%. WineFS suffers from 30x fewer page faults in this workload compared to Nova. We next answer the second question of evaluating the POSIX system call performance of WineFS. We measure the performance of WineFS when freshly formatted on a wide variety of applications that use POSIX system calls. The performance of system call applications does not degrade with age for any file system, since it does not depend on the fragmentation of free space. We measure the throughput for each file system with respect to ext4 DACs. WineFS equals or outperforms all other file systems on all of the system call applications. To conclude, WineFS demonstrates that it is possible to design a file system that achieves high performance for new memory mapped applications, achieves high performance and scalability for legacy POSIX applications, and maintains this high performance in the presence of aging and under high utilization. We have open sourced WineFS on GitHub, and we encourage you to try it out. Thank you for attending my talk, and I'm happy to answer any questions in the Q&A or chat session. Thank you.